Hello students, in this video I will go through the process of finding the area of regular polygons. Alright, so before I go into finding the area of a regular polygon, I just want to maybe revisit the area of a triangle. So the setup here is slightly different, okay, from the type of finding the area of a triangle problem that you typically would be given. Typically, in the past, you would be told that that the triangle would be a right triangle, and you would be given the dimensions of the triangle, right? And in this case, then the area here would simply be 1/2 base times height, right? And this would be 6. And how do we know that this would actually be the area of the triangle? Well, that's because the 3 here has to be the altitude because of the fact that we have a 90-degree angle there. Here in this case, you're told information about the triangle. You're given other information. You're not given the height of the triangle. So what are you going to do in a case like this? Well, anytime that you're trying to find the area of a triangle, you always have to fall back on that fact that the area of a triangle is 1/2 base times height. You need to know the height of the triangle. I mean, I hate to break it to you. All the fancy formulas, okay, that are developed are always based on fundamental math, based on fundamental ideas. So how are we going to find the area of this triangle if we are not given the height of the triangle? Well, in order for us to find the area, let's find the height. So to find the area, let's first find the height of the triangle by using a little trig. All right. So I notice now, okay, by making this drawing, what I have here. Whoops. What I have here is a right triangle. See, I'm always falling back, like whenever you're problem solving in the future, you're always falling back on things you already know, right? Or things that you're familiar with. And from there, you can make further conjectures. So we have this right triangle, and what we can do is we can set up a sine relationship, because I know that h here is opposite of 50, and 3 here is the hypotenuse. So that's what I'm going to do. I will say that h over 3 is equal to sine of 50. And I can then solve for h. H is then equal to 3 sine 50. And punching that into the calculator, I can get a decimal value, or actually, I didn't do that yet, I'm sorry. So now that I know the value of h, and I know the base here is 4, I can then get the area of the triangle, which is 1/2 4 times 3 sine 50, and punching that into the calculator, now I will get a decimal value of approximately 4.6. Alright, so let's try to summarize this or generalize this process a little bit to help us find the area of a triangle if, in the case, we're not given the height of the triangle. So let's say here now I have a length of b and a length of a, and the included angle here is theta. All right. And we're going to go through a really similar process. In order for you to find the area of the triangle, we have to first know the height of the triangle. So again, let's use some trigonometry to find the values of h in terms of a and theta. I cannot find h in terms of b because notice right here, b is partitioned, right? I don't have a full length of, I do not have a full length of, or I don't know like what portion to break up b into. So that's why I'm not going to use b or involve b to describe h. So I know that, again, h over a is equal to sine of theta. Solve for a. H is equal to a sine theta. And once again, area of a triangle is 1/2 base times height. And because of this, I can then make the substitution that the area is 1/2 base times, instead of writing height, a sine theta. Or area of a triangle is really 1/2 ab sine theta. This is a really important equation for, or the area of a triangle. notice the information that's given, or not given. Notice that the information that you need to have in order to find the area of the triangle here. We no longer need the height. However, we do need to be given at least one other side and the included angle. Okay, so this is actually a big jump. So you know what I was saying a moment ago? We always fall back on things that we knew in the before, and then we make inferences. Well, this is a direct example of that, where again, knowing the area of a triangle is 1/2 base times height, we then developed a more advanced form for finding the area of a triangle. And you're going to practice this in some of the exercises that I'm going to assign associated with this lesson. So let's try to extend this idea a little further, okay? So now that we know how to find the area of pretty much any triangle, but you have to be given an SAS relationship, let's try to extend that idea to finding the area of a polygon. So for our example, what we're going to do is, and the idea expressed in this example I'm about to go through with you can be applied for any n-sided polygon. Okay, so for this particular example, I'm dealing with an octagon with a side length of 5 inches. And what we're going to do is we're going to try to find the area of this octagon by utilizing things that we're familiar with. Okay, so recall that that a regular polygon has rotational symmetry, right? In order for us to, well, rotational symmetry meaning that the regular polygon, when rotated, will land exactly on itself again, right? With that said, when something has rotational symmetry, in particular for a regular polygon, if we were to connect vertex to vertex, what we will end up forming is congruent isosceles triangles. So by doing this, okay, if we find the area of one isosceles right triangle and multiply that by n number of sides, we will then end up with the area of the polygon. So in this case here, let's first find out what the dimensions are of one of these isosceles triangles. So I know that theta in this case, right? To find theta, all I have to do is take 360 and divide by the number of sides I have, which is going to be 360 over 8, which turns out to be 45. I will need to focus my attention on this triangle here, which is one of the triangles inside of the octagon that I've broken up. So let's find out some of these dimensions. Let's find out what angle x is, okay? Because what I need to do is I need to find out one of the side lengths. So to find out what angle x is, I know that 2x plus 45 is equal to 180, right? Because this whole triangle here, right, 2x plus angle theta, right, 2x plus angle theta will equal to 180. Solving for x, I end up with x is equal to 67.5. And if I were to find the area of this triangle, if I know the two sides, if I know side A, then therefore I'll know also side A. And if I know those two sides, and I already know the included angle, I can apply the formula that we just developed a moment ago. So let's find out what is side length A. Side length A can be found by using a little bit of trig. I know that 2.5 is adjacent to angle x. I know that I want to find out what angle A is. I mean, not angle A, side length A is. So because of this, I will end up with a cosine relationship. Right? 2.5 over A is equal to cosine of 67.5. Now, did we actually have to find out what angle x is in order to do this? No, of course not. there are other ways of working around this. This is just my interpretation. This is just the way that I'm approaching this. Certainly there are other methods of going about this. So I want to try to isolate A here. If I isolate A, I'll end up with A is equal to 2.5 over cosine of 67.5. I punch this into the calculator. Try not to round until the very, very end. So I have approximately 6.533. Now I know what A is, and recall that the area of a triangle is either 1/2 base times height or 1/2 AB sine theta. I know what A is. I can find the area of this triangle. So therefore 1/2 A squared, right? Because I'm using A and A. I'm using A and the included angle. So 1/2 A squared times sine of 45, that will give me 1/2 of 6.533 squared sine 45. So the area of one of these isosceles triangle will turn out to be approximately 15.1. And since I have 8 of these isosceles triangle, I multiply that area by 8, and I get 120.8. I want to quickly go through alternatively, right? Did we need to figure out what A was in order to go about this? Did we actually have to use this formula to figure out the area of this octagon? No, like I was saying a moment ago, there are different ways of approaching this, and this is just my way of doing it. So alternatively, right, you could have also figured out what H was. So let me just show you that we'll end up in the same place. You can find out what H is instead of A, and by finding out what H is, we can then use this formula here instead. So to find H, what we're going to do is we're going to say H over 2.5, right, assuming that we didn't find A, right, H over 2.5 is equal to tangent of 67.5. It's tangent because H is opposite of X and 2.5 is adjacent to X. That's why we're using tangent. H will then equal to 2.5 times tangent of 67.5, which approximately equals to 6.0355. Let's take this information, right, what H is, and the overall base, which is 5, and apply it into the formula 1/2 base times height. I'll end up with this value. Area is equal to 1/2 times 5 times 6.0355, which comes out to approximately 15.1, to no surprise. We should have ended up with the same exact answer, in which we do. So again, the area of the isosceles of the regular octagon here turns out to be 120.8 inches squared. So again, no different.